we're going to work, in this video, we're going to work 7 stoichiometry problems. If you're really trying to master this, then go watch the previous video where I talk about the basic procedure to do stoichiometry. I talk about the mole method, stoichiometric equivalency. Watch that video. Once you have a general understanding of the procedure for doing this, then come back to this video, pause before I work each problem, try it on your own, give it your best shot. If you can't figure it out, sit there and think about it. Once you've thoroughly tried to figure it out and you can't get the answer on your own, watch the solution, see what you did wrong, go to the next problem, pause it, try again. By the 4th or 5th problem, you'll start to get the right answer. By the 6th or 7th problem, you'll know exactly what you're doing. So let's get started. Silicon tetrachloride, SiCl4, can be prepared by heating silicon and chlorine gas, given by this reaction. In one reaction, 0.507 moles of SiCl4 is produced. How many moles of molecular chlorine were used in the reaction? Okay, so the first thing you want to do with these problems is you're going to be given an amount of something. You have to be, because you have to have something to start with. They tell us that 0.507 moles of SiCl4 is produced. So first, just write that out. Now we're going to use the stoichiometric equivalencies to find what the question is asking. It's saying how many moles of molecular chlorine were used in the reaction. Well, from stoichiometric equivalency, we know that, in the mole method, we know that for every 1 mole of SiCl4 produced, 2 moles of Cl2 were used. And so that's what we're looking for, the number of moles of molecular chlorine. So that's our units. So we just need to do this multiplication. 1.014 moles of molecular chlorine. Certain race cars use methanol, which is this, also called wood alcohol, as a fuel. The combustion of methanol occurs according to the following equation. Okay. In a particular reaction, 9.8 moles of CH3OH are reacted with an excess of O2. Calculate the number of moles of H2O formed. All right. So again, what are we starting with? We're starting with 9.8 moles of CH3OH, and then we're going to go through conversion factors to get to our final answer. We start with what we're given, and then we use the conversion factors, the stoichiometric equivalencies, to get to what they're asking us. And the stoichiometric equivalencies, we can, all of these are stoichiometrically equivalent to each other. Go watch the previous video where I explain that more clearly. Okay, so an excess of O2. So yeah, this is just telling us that we have 9.8 moles of CH3OH. We all 9.8 moles are consumed. If you didn't have enough O2, then you would only consume some of these 9.8 moles. So this is just this statement here is just telling us that all 9.8 moles are converted to products. Okay? So what is it asking us? Calculate the number of moles of H2O formed. All right? So we know that for every, using stoichiometric equivalency, we know that for every 2 moles of CH3OH consumed, 4 moles of H2O are produced. Okay, and then this cancels, so it's just 2 times 9.8. 19.6 moles of H2O. Are produced. when baking soda, so sodium bicarbonate or sodium hydrogen carbonate, NaHCO3, is heated, it releases carbon dioxide gas, which is responsible for the rising of cookies, donuts, and bread. Part A, write a balanced equation for the decomposition of the compound. And then part B, calculate the mass of NaHCO3 required to produce 20 grams of CO2. All right. Part A, write a balanced equation. So what is it telling us? So baking soda is going to be heated. So we're in our reactants, we're going to have baking soda for sure. Okay. And it's just saying when baking soda is heated, it does something. So like it's not reacted with anything. It's not saying when baking soda is reacted with this, it's just heated. So it's just NaHCO3 is heated. So maybe, you could almost put heat, something like that. It releases carbon dioxide gas. So it releases CO2, and also another product is Na2CO3. Okay, so there we go. Now let's just balance this. So there's two NAs on the right. Well, wait. Okay, hold up. We need to have hydrogens on the right. So I'm assuming, I'm not a chemist, but I guess just H2O gas or something. I mean, it could be H2 gas, just like hydrogen gas. But I'm thinking it's H2O. So let me check the answer. Yeah, so it's going to be H2O. So this is the unbalanced equation. So now let's balance this. We've got two NAs on the right. Now we've got two NAs on the left, sodiums. We've got two hydrogens on the left, two hydrogens on the right. We've got two carbons on the left, two carbons on the right, and we've got six oxygens on the left and six oxygens on the right. Okay, there we go. So that's part A. Part B, calculate the mass of NaHCO3 required to produce 20 grams of CO2. All right, so with stoichiometry, you first write out what you're starting with, what you're given. They're telling us 20 grams of CO2. Now we're going to use those conversion factors and to work our way to what they're asking, which is the mass of NaHCO3. All right. So we use the mole method, that like the stoichiometric equivalencies, for every 2 moles of this consumed, 1 mole of CO2 is produced. For every 1 mole of CO2 produced, 1 mole of H2O is produced. We use those with moles, not with grams. So to interconvert, we're trying to get to not CO2, we're trying to get to this molecule. So we need to convert this to moles, switch to this molecule, then convert back to grams. How do we do that? How do we convert from grams to moles? We use molar mass. So let's calculate the molar mass of CO2. So this MCO2 is equal to, so the atomic weight of carbon is 12.011 plus 2 times the atomic weight of oxygen, 15.999. Okay. $44.009. Grams of CO2 per mole. Okay, so now just use this. This is a conversion factor. It's like we talked about in the previous video. 12 inches is equal to 1 foot. You can use that in this way. It's like we know that 44.009 0.009 grams of CO2 because we want this to cancel per 1 mole of CO2. That's how you read this. Molar mass is in grams per mole. Grams of CO2 per mole. Grams of CO2, 44.009 grams of CO2 per 1 mole of CO2. So these cancel out, and now if we just stopped here and did this multiplication, we would have the number of moles of CO2 corresponding to this 20 grams. But that's not what we're looking for. Okay, we're trying to get the mass of NaHCO3. Okay, this. Well, how is, if 20 grams of CO2 are produced, how is that related to this? Well, okay, the stoichiometric equivalency for every, so we're looking at these coefficients, for every 1 mole of CO2 produced, 2 moles of NaHCO3 were consumed. These cancel. Boom. Now, if we did this multiplication, we would know that to produce those 20 grams of CO2, this many moles of NaHCO3 were consumed. Are we done? No, because where are we trying to get? The mass of this. So we need to keep going. How can we get mass? If we have moles, how can we get mass? Use the molar mass. That relates grams and moles. So now let's get the molar mass of NaHCO3. All right? Atomic weight of sodium, 22.99. Okay. Hydrogen, 1.008. Carbon, 12.011. And then 3 times oxygen was 15.999. Okay. $84.006. And what is this? This is grams of NaHCO3 per mole of NaHCO3, per 1 mole. All right, so let's just use this conversion factor. We want to put the moles of this in the denominator to cancel out this. So it's 1 mole of NaHCO3 for every grams. Okay? See, these cancel. Now we're left with grams of NaHCO3. That's what we're looking for. Done. So, well, not done. Let's just do the multiplication. So 20 times 2 times 84.006 divided by 44.009. 76.4. What are our units? Grams of NaHCO3. So that's the answer. It was you needed 76.4 grams of NaHCO3 in order to produce this 20 grams of CO2. Fermentation is a complex physical process of wine making in which glucose is converted into ethanol and carbon dioxide according to this chemical equation. Starting with 500.4 grams of glucose, what is the maximum amount of ethanol in grams and in liters that can be obtained by this process? So we've got our chemical equation, and you need that to start. To do stoichiometry, you need a balanced chemical equation. Once you have that, again, write out what you're starting with, what you're given. We've got 500.4 grams of glucose, which is this. This is Okay. Now we're going to convert. We're going to use our conversion factors, our stoichiometric equivalencies, to get to where we want to get. Where do we want to get? What is the maximum amount of ethanol in grams and in liters? So once we get ethanol in grams, we can just easily convert that to liters with this. But let's just get to ethanol in grams first. That can be obtained by this process. So if all 500.4 grams of glucose are converted to products, how many grams of this do we get? Okay, so we need to convert this to moles. Once we have the amount of moles of glucose, we can use the mole method to get to the moles of ethanol. Then we can convert the moles of ethanol to grams. We'll have that the first answer. Then we can convert to liters with this. So how do we convert grams of glucose to moles of glucose? We need the molar mass of glucose. Okay, so C6, 6 times 12.011, okay, plus H12, 12 times 1.008, plus 6 times 15.999. All right. $180.156. Grams per mole. Grams of C6H12O6 per mole. Okay, so let's use this to convert to moles. So we've got 180.156 grams of C per mole. So now we've got the moles of glucose. So now let's convert to moles of ethanol. So we know that for every 1 mole of glucose consumed, 2 moles of ethanol are produced. Okay, now we've gotten to moles of ethanol, but we want to get to grams of ethanol. And then once we're at grams, we could also get to liters. Okay, so, all right, now we need the molar mass of ethanol. Okay, so we've got 2 carbon atoms, and carbon was 12.011. You've got 5 hydrogens, or 6 hydrogens. And 1 oxygen. Okay, so $49.069 grams of C2 per mole. All right, so this is telling us that for every 1 mole of C2H5OH, we've got 49.069 grams of C2H5OH. Okay, so now we're in grams of C2H5OH. So let's calculate this, because that's one answer we're looking for, the amount of ethanol in grams. So 500.4 times 2 times 40 9.069 divided by 180.156, 272.6 grams. Okay, so that's the starting with 500.4 grams of glucose. If all of that is consumed, then you end up with 272.6 grams of ethanol. How many liters of ethanol is that? All right, so let's write out what we have. Okay, so we know that we have 0.789 grams of ethanol per milliliter of ethanol. I'm not going to write ethanol, but we know this is the density for ethanol. Okay, so all right, but they're asking us in liters, so we need to do another conversion, and we've got 1,000 milliliters for every 1 liter. I don't know. Okay, so now we can do this. So 272.6. Why did I cross this? What am I doing? I don't know why I'm across the whole numeric value out. So all right, divided by 0.789 times 0.35 liters. 0.35 liters of input of ethanol. For many years, the recovery of gold, that is, the separation of gold from other materials, involved the use of potassium cyanide. And so the separation of gold from other materials, they give us the chemical equation. What is the minimum amount of KCN potassium cyanide in moles needed to extract 29 grams of gold? All right, so they give us 29. We're starting with 29 grams of gold. Okay, now we're going to use our stoichiometric equivalencies to get to where we want, starting here. So this is kind of confusing because I feel like this is a reactant, right? You're starting with gold in other materials, then you do the separation, and you wind up with what you want, just gold by itself. So, but anyway, the minimum amount of potassium cyanide, that's saying, so according to this reaction, for all 29 grams of gold to be used up, how much potassium cyanide do you need? So we're going to convert this grams of gold to moles, then use stoichiometric equivalency to get to moles of potassium cyanide, and then we're done. They're not asking us for grams of potassium cyanide. So, all right. So what is the molar mass of gold? 196.97. Grams of gold per mole. Okay, so 196.97 grams of gold per 1 mole of gold. All right, now let's use our stoichiometric equivalencies. According to this equation, for every 4 moles of gold consumed, 8 moles of potassium cyanide are consumed. Okay, and we could do this, and that's it. They're not asking us for to go any further. So 29 times 2 divided by 196.97. 0.29 moles of potassium cyanide. Nitrous oxide, also known as laughing gas, can be prepared by thermal decomposition of ammonium nitrate. The other product is H2O. Write a balanced equation for this reaction. And then how many? Okay, so let's just part A, write a balanced equation. So this nitrous oxide is prepared by the thermal decomposition of ammonium nitrate. So it doesn't, you're not reacting ammonium nitrate with anything. It's just like it's just thermal. So that sounds like to me is that it's just going to be, that's going to be the only reactant, and this would be, you just add heat and that, and then this decomposes. Okay, and what's produced, one of the products is the laughing gas. Another product is H2O. All right. Are we missing anything like an H? And yeah, that looks like it's it. That's it. Okay, so now we need to balance this. So N2, now we have two nitrogens on the left, or no, we already had two nitrogens, so N2, good. H, we need a 2 here maybe. So we've got two nitrogens on the left and the right, 4 hydrogens on the left and the right, and 3 oxygens on the left and the right. Okay, there we go. That's part A. Part B. How many grams of N2O are formed if 0.46 moles of NH4NO3 is used in this reaction? Okay. So they're telling us that 0.46 moles of NH4NO3 are used. So we're going to go from this to grams of N2O. 0.46 moles of NH4NO3 are consumed. All right, so now we're in moles, so we're trying to go to N2O, so we can say that for every 1 mole of NH4NO3 consumed, we've got 1 mole of N2O produced. All right, but now we need grams of N2O. So to convert here, we need the molar mass of N2O. So 2 nitrogens, 14.007, plus 1 oxygen, 15.999. Okay. .013. That's grams of N2O per mole. Okay, so using this, we can say that for every 1 mole of N2O, you have 44.013 grams of N2O. Okay, and now that's what we're looking for, grams of N2O. 0.46 times 44.013. 20.2 grams of N2O. A common laboratory preparation of oxygen gas is the thermal decomposition of potassium chlorate. Assuming complete decomposition, calculate the number of grams of O2 that can be obtained from 46 grams of KClO3. All right, so another thermal decomposition type of reaction. So thermal decomposition of KClO3. So we need to get our balanced chemical equation first. You can't do stoichiometry without a balanced chemical equation. Okay, so it doesn't say that you combine two molecules and then add heat. It just sounds like you're just taking your compound here and adding heat. All right, and so we're going to be decomposing into definitely O2. And then what else? The products are, it tells us the products are KCl and O2. Okay, so how do we balance this? We've got one potassium on the left and the right, one chlorine on the left and the right. We've got 3 oxygens on the left, 2 on the right. So what we do is, if you remember back to the videos where we talk about balancing chemical equations, first of all, having an having an element by itself is very powerful, because once you balance every other element, then you're pretty much done, because you can do this. I could say, okay, I need 3 oxygens on the right. So there you go. We have 1 potassium on the left, 1 on the right, 1 chlorine on the left, 1 on the right, 3 oxygens on the left. 3/2 times 2 is 3 oxygens on the right. But you don't want to have a fraction as a coefficient. So let's multiply this entire equation times 2. So we've got, okay, so 3, and this is balanced. So now we can do stoichiometry. What is it? What are we starting with? 46 grams of KClO3. Okay, now we're gonna work our way over to what? The number of grams of O2. We need to get to moles here, so we can then convert to moles of O2. So to convert from grams of KClO3 to moles, we need the molar mass of KClO3. Potassium, 39.098. Okay, chlorine, 35.45. And then oxygen is 15.999. Okay, so $122.545. And what is this? This is grams KClO3 per mole. All right, let me move this. So now, we have 122.545 grams KClO3 per. Okay, these cancel. All right, now we're in moles of KClO3. We know that according to our chemical equation, for every 2 moles KClO3, 3 moles of O2. For every 2 moles of KClO3 consumed, 3 moles of O2 are produced. And that's what we're looking for, O2. Okay, but we want to get to grams of O2. All right, so now we need the molar mass of O2. This is 2 times 15.999 31.998. This is grams of O2 per mole. All right, so 31.998 grams of O2 per mole, 1 mole of O2. There we go. So now we've got everything we need to get the grams of O2. Just do the multiplication. So 46 times 3 divided by 2 divided by 122.545. 18.02 grams of O2.